Hello, my name is Henry Sham. I am going to present to you this work developed in collaboration with Aurélie Clodic and Rachid Alami. Joint attention is a fundamental skill studied in several fields of cognitive sciences. JI could help to investigate HRI situations mediated by objects and entities where multiple humans and robots could interact simultaneously. JI is also an important component for understanding joint action and underlying intuitive forms of communication between partners, which is very relevant to HRI. We study JI as a set of cognitive processes and skills allowing individuals to focus on physical objects and others. As shown on the table at the right, JI constitutes qualitatively distinct types of social attention along with corresponding levels of common knowledge. A scale of jointness in sharing attention and knowledge has been hypothesized in the literature based on the access or perspective to experience oneself and others. At the left extreme of the scale, as shown in the figure, there is individual attention or no jointness. The level of sharing gradually increases, moving at the right of the scale through four social attention types, which are monitoring, common, mutual, and shared. We propose to model JI based on the following assumptions. Firstly, the perception and representation of JI constitutes an isomorphic relation in a Gestalt sense. This hypothesis is illustrated at the right, where neurons are arranged in a topology encoding locally information of attention and knowledge sharing according to an increasing order in jointness. Secondly, inspiration in dynamic neural fields theory is a promising way to investigate contextual and nonlinear spatial-temporal relations underlying attention and knowledge sharing in HRI. The model architecture is presented in this slide. The lowest layer is provided with observations regarding each participant. Layers represent individual, social, and group features. Finally, the topmost layer encodes the scale of jointness for each pair of agents. Features are mostly modeled as scan networks. Some features are obtained, though, from the projection of subnetworks representing logical operations such as AND and OR. Here I present to you the model of a continuous attractor neural network. The activation age of each neuron in the layer encodes information within a topological space ensured by lateral connections considering a firing rate f. The matrix W represents local interconnections where interaction strength is chosen, so similar states have stronger connection. For top jam, Gaussian weights were set around reference values in the model topologies. Finally, external input is modeled through the vector U. This set of equations define how the activation of each unit of the scale of jointness receives an external input information from individual, social, and group features. The arrow notation is used to denote levels of features intensity in unidimensional topological space. The experimental scenario is illustrated at the left. Several objects were placed in a round table where two subjects interacted with a humanoid robot, Pepper. Behavioral data was captured through a Qualisys motion tracking system as shown at the right. Markers were attached to the eyeglasses frames and the shoulders for tracking the posture. Subjects were instructed to direct the head towards particular objects or other agents, so defining postures or behavior frames within a situation. The robot was programmed accordingly in closed-loop control. The experimenter signaled subjects to switch between frames and triggered the robot to do so. We first programmed a simulation for testing the model. Under several conditions, noise was added to input variables from multivariate distributions. Here I show you the experimental results for the situation at the left. The time evolution of the joint attention state for each pair of subjects is shown at the right. An instantaneous capture of the monitor tool developed for Top Jam is shown at the right. The activation of units is illustrated through color transparency. As noticed, the information encoded by the model has the potential to be read directly in terms of levels of intensity. I invite you to consult supplementary resources regarding the project. We proposed a model named TopJam to represent joint attention states for HRI inspired by research in human social cognition. TopJam is modeled as a dynamical system relying on a hierarchy of CANs network structures. The model can be integrated to existing HRI decision and control architectures as a dedicated component for JI. The project is developed as open source technology for robot standards such as ROS. The model is computationally feasible for real-time operation in small scenarios such as the office or home. The representation has also the potential to be directly understood by humans. Interesting research perspectives are integrating observations on speaking behavior and pointing gestures to the model. A general production rule framework is under development, having the potential to help further prototyping with TopJam. Automatic selection of parameters is possible given the model is differentiable. And finally, considering not only behavioral but also electrophysiological data. Thank you very much for your attention and for these institutions which allow the accomplishment of this project.